in this lecture we are going to talk about the digital current mode control design and Matlab case study in a buck converter. So, we will talk about design case study of digital current mode control buck converter and then Matlab simulation of digital current mode control. So, here we want to recapitulate our analog current mode control structure, and that we have discussed multiple times. So, this is the structure and this is we are considering peak current mode control fixed frequency, that is under trailing edge modulation. Then what is the primary loop shaping objective in analog current mode control? So, we consider the control to output transfer function, and this we have discussed in lecture number 36, 37, I think 38, yeah, lecture number 38 in our earlier NPTEL course for current mode control design in a buck converter. So, where so this is lecture number 38 in our NPTEL course. So, where we know that current mode control can be, now buck converter can be approximated, control to output transfer function can be approximated by a first order model, and then by stable pole 0 cancellation we can design a compensator which, so if you take a PI controller, then this is the case when we are ignoring the effect due to ESR, assuming that ESR is very low, which is typically the case for a practical converter. If ESR is there, we have shown that we need a type 2 compensator where, and if the ESR is negligible, then a PI controller is enough. So, what is difference between PI and type 2? We have discussed the type 2 compensator is a generalized version of a PI controller where we can have an extra pole, and if we keep that extra pole far left hand side, then it can be approximated like a PI controller. So, if we consider an ideal buck converter, that means a very low ESR, then we can consider a PI controller. And what is the design objective? The omega CZ, that means the PI controller can be represented by this form where the 0, it has 1 0 and 1 pole at origin, the 0 is Ki by Kp, and then if we take the loop transfer function by stable pole 0 cancellation, then we will get the loop transfer function is a first order system, and this require that controller 0 should cancel the pole, and it turns out the proportional gain should be Ki times Rc, because we are assuming the ESR to be negligible. So, it is R is the load resistance and C is the output capacitor, and this we have discussed in lecture number 44. Now, if we want to get the digital controller, then how to design? So, we will start with the crossover frequency 1/8 of the switching frequency, and we know that in traditional current mode control by stable pole 0 cancellation we can achieve the loop transfer function some gain by S, that means we will get 90° phase margin, but due to the delay in the digital controller the phase margin will be lower than the analog controller, and that will be 90° minus omega c times tau d, where omega c is the crossover frequency. So, we suppose our desired phase margin is 60°, and if you try to push the crossover frequency and the delay is large, so this term can be significant. So, we need to check that for given tau d what we need to meet certain 60° phase margin. So, that will pose a limit on your crossover frequency. You cannot have a very large crossover frequency due to the phase lag contribution, which may reduce the effective phase margin. Another aspect, we cannot increase crossover frequency too high, because we know that if we try to cross in current mode control the crossover frequency beyond 1/8 or so, then our model validation is an issue. So, the small signal based design may not be valid beyond that. So, keeping those two facts in mind, our desired objective to achieve 60° phase margin without violating the model validation problem. So, if the phase margin is lower than 60°, then we have to reduce further this omega c, and so that it pass this third requirement, and if it is passed, then we will go to the last step, that our controller gain integral is simply crossover frequency by R. Once we get, that means we can get the PI controller gain. So, that means this is our analog PI controller, and analog PI controller Kp value we know it is Ki time Rc, and Ki equal to crossover frequency by R, and whatever the crossover frequency select, we select typically crossover frequency will take 2 pi the switching frequency by roughly 8 or so, because in current mode control we can get somewhat higher than the voltage mode control, and that divided by R is the Ki. Once we get the continuous time proportional and continuous time integral gain, then the derivative digital Pi Kp gain will remain same, but digital integral gain will be analog integral gain multiplied by the sampling time. So, this we have discussed in lecture number 44 in this course. Now, we want to see some Matlab case studies. So, let us go back to the Matlab, and this is a mixed signal current mode control. I think that we have discussed in week 2, how to implement mixed signal current mode control. If we go inside, we have also discussed that mixed signal current mode control with a custom PI controller block with a clock synchronized operation, that also we have discussed in the 3rd week lecture. Then we need to set the right value of the proportional gain and the discrete time integral gain. So, then there is another option is the load current feed forward, we may or may not use, and I will take both the case studies. So, initially we will take the feed forward, load feed forward to be 0, then it will be the traditional current mode control, peak current mode control. Then if we consider KFF to be 1, there is a perfect load feed forward, and we want to see what is the response. So, let us go back to the design methodology. So, if we consider the traditional current mode control design, and we are assuming that ESR to be very small, so we are not going to compensate ESR. So, we are taking a simple PI controller, and we have already discussed the PI is nothing but the integral gain is nothing but 2 pi, then your crossover frequency, that means it is basically crossover frequency by R. So, this whole term is the crossover frequency in radian. So, if we set the crossover frequency or the bandwidth is, let us say 50 kilohertz, it is in kilohertz or 80 kilohertz, accordingly the gain will be calculated. Then we are finding the numerator gain, which is the denominator of this, because we are doing some stable pole 0 cancellation. And what is denominator of C? It is nothing but denominator C, it is nothing but it consists of the pole of the first order approximated model of the buck converter under current mode control. So, that will be the numerator, and denominator is nothing but simple integrator at origin, that means a pure integrator. So, in this case the Ki is this, Kp is we have discussed Ki time R into C, R is the load resistance. The discrete time Kp gain will remain as the proportional, the analog controller gain, but the discrete time integral gain is the continuous time integral gain into the sampling time, and then these parameters will be set in the digital controller and we want to compare. So, let us first consider, and we are initially considering no feed forward of the load current. So, it is 0. So, let us consider. So, it will ask for the bandwidth. So, let us set the bandwidth to be let us say 80 kilohertz. Then it will show the response, and before going to that we will go to the Matlab and see the loop transfer function. So, here we will set the loop transfer function and limit we will set. Then we want to see all the stability margin. So, you can see we are getting 80 kilohertz is your crossover frequency, and the phase margin is 96.4, much higher phase margin, because actually ESR is there, though we have ignored, but it is at high frequency. So, due to that it will give a phase boost, okay, because we are not exactly cancelling, because we are not anticipated ESR, but that is fine. So, now we are getting phase margin, then but when you go to digital control we will have one additional lag, and the phase delay is how much? Here 0.9 time t, that means we are taking the sample first and then switching, and this duration is 0.1 t, that means t by 10. So, we are taking a sampling delay of t by 10, because it is first sampling then switching, and that actually will give rise to some kind of phase lag. So, then if we go to the response, this is the inductor current and this is the output voltage. So, here you can see the output voltage, red one is the sample voltage, and I want to show you, if you consider the sample voltage, you can see we are taking the sample first and then switching. So, there is a T/10 delay, and this delay will cause some additional phase lag compared to analog control. Now, the next task once we do, we want to compare what will happen if we add a load feed forward. So, in that case we will simply not show the sample. So, let us first simulate once more, that means 80 kilohertz. Now, we do not want to show the sample signal. So, this is the output voltage without load feed forward, and this is the inductor current. Now, we want to go for load feed forward. So, let us use 1, and we have used 80 kilohertz is the crossover frequency. Now, we want to rerun this simulation, and we want to hold the previous value and change the color of the plot. So, we are using red color for plotting the current and voltage for this case. Now, we have added the load feed forward. So, again we are giving 80 and see what happened. So, you can see because of the load feed forward, the response is extremely fast. You can see this is extremely fast. It is like almost like time optimal. That means you can see the inductor current will come back red color. It is not exactly time optimal, but so because there is no load feed forward, so there was an initial delay in the voltage, and that was causing one of the issue with the additional undershoot. So, this is because we have applied a load step at the point of switching, and sample for that signal was captured here. So, it did not recognize the delay. So, that means it was showing like almost one full cycle delay. The inductor current has not responded to the transient. So, transient is applied here, but the sample is captured somewhere at this point. So, that is why sample, after sampling, the peak current does not know that there is a transient here. So, it is almost like a one cycle delay, and that is why you will get an additional undershoot. Whereas, if you add a load feed forward, the peak reference will automatically get set, because it is actually as if we are subtracting the load current from inductor current, or we can add the load current with the reference current. So, the reference current will get automatically shifted by this load feed forward. But it may be difficult to sense load current in practice, because it is not permissible, but in many cases if you take LED driving case study, or maybe if you can interact the processor information, you can make the output impedance as well as the load transient response extremely fast, or output impedance to be very low, it can make it by means of load feed forward. So, in summary, what we want to discuss that, we want to go back. So, we have considered that because of the delay, you will get some additional, because it will take time to respond. So, that is why in many commercial products, they try to increase the sampling frequency during transient to speed up. Another way, they can use an analog comparator by means of a voltage hysteresis, so that if the voltage goes beyond this band, then they can either increase the sampling rate, or they can suddenly create a step reference to actually anticipate the load transient effect. So, there are many ways of, because in the subsequent lecture, in the next lecture, we will be discussing how to go beyond this small signal design, so that you can get a really very fast transient. Because the digital control, if you look at the small signal based design compared to the continuous time control, it actually gives rise to additional delay. So, the digital control may not be an useful solution if you go by small signal design, but the digital platform offer you to change the controller gain based on the operating point. That is the only advantage, and adaptive dead time. But unless you implement some more advanced logic, this digital control may not be so useful, and that is why majority of the commercial product are going with some nonlinear or some other large signal based design, where you can actually capitalize this digital controller, and you can also introduce some tuning as well as advanced algorithm. In summary, we have discussed the design case study of digital current mode control buck converter, and we have also considered some simulation case studies, and we have shown that how to design using small signal digital current mode control. But this lecture will show that this is not the superior way of digital control design. So, in the subsequent lecture we will slowly tend towards the large signal based design and show that the performance can be much faster by utilizing the trajectory information as well as some advanced control algorithm. We can achieve close to time optimal solution, and that is the future trend of digital control. But here we want to finish the small signal based design methodology. We have already discussed the small signal based design for voltage mode, and this lecture we have discussed the small signal design case study of current mode control. Now we will go for large signal based design in the subsequent lecture. That is it for today. Thank you very much.